So hi everyone, my name is Yulia Mikhailova. I am with Princeton University. I lead the Extreme Light Meta Interactions Lab here. And it's a great honor to give an invited talk at this conference. Thank you very much for inviting me. And I really appreciate you took the time to be here today. So let me share my presentation. Share. All right, you see it, right? So the title of my talk is rather general, plasma optics for novel sources of bright light, but I will focus my presentation on relativistic plasma mirrors today. So plasma optics, transient plasmas, which are produced by laser pulses in solids, gases, liquids, they can be used as efficient linear and nonlinear optical components. They have, these plasmas have very special responses to light field. They are broadband, their responses are ultra fast, and they are highly nonlinear, which makes them really efficient in light manipulation. So plasmas, laser-produced plasmas can handle very high laser intensities. They can be switched on and off by laser pulses at very short time scales, picosecond, femtosecond. And then they can be used to, and they were shown already to be capable to redirect and focus light, diffract, split and combine light beams, polarize, change light polarization, create holograms, temporally and spatially filter intense light, and very important, also generate new frequencies of a broad spectral range from terahertz to ultraviolet, to extreme ultraviolet, and X-rays. Today I will talk about plasma mirrors, and in particular relativistic plasma mirrors. What is this? So if we shine an intense laser with intensity of more than 10 to 16 watts per square centimeter for 800 nanometer light titanium spy laser, if we focus it on a solid density target, glass, for example, or liquid jet, we ionize the target almost instantaneously if the temporal contrast of our pulse is good enough. And this plasma, it's a very special plasma. It's really tiny and it's really ultra fast. So the world of these plasmas is ultra fast and ultra small. So these are very, very small reflectors. So the size of these plasmas is about is of the order of microns, and the dynamics of these plasmas happens on the femtosecond and picosecond scale. So what is even more interesting that the relativistic electron bunches, when I say relativistic, it means that they are moving with speeds close to the speed of light. These electron bunches, which are formed and accelerated near the surface of the target in these plasmas, their world is even smaller and even faster. So they are nanometer sized, and their dynamics happens on attosecond time scale. So these electron bunches are very important for us because they give rise to a variety of very interesting and potentially very useful phenomena. So the plasma mirrors are capable of handling very high laser intensities, much higher than the optical breakdown threshold of traditional optical components. So these plasma mirrors can be used as mirrors for ultra intense light. They can steer light, they can focus light, and they can also temporal and spatial filter light. For example, they can clean temporal contrast of laser pulses, ultra-short laser pulses. And again, maybe the most interesting feature, they are really powerful. We hope they are really powerful in frequency conversion, and especially interesting in coherent high harmonic generation. So what are the so-called relativistic harmonics from plasma mirrors? So if we now boost the intensity of laser light on the plasma mirror and make it larger than the so-called relativistic intensity, the intensity at which electrons in the light field move with the speed faster than close, or not faster, close to the speed of light. So that's about 10 to 18 watts per square centimeter for titanium sapphire laser. So when intensity in the focus is higher than this value, the electron bunches formed at the surface of the plasma, they become highly relativistic, and the light reflecting from this plasma, I forgot to mention that this plasma is very, very high density because everything is fully ionized and the density of material is really high. So these plasmas reflect light, almost all of it, and in reflected light, we see this very distorted field, sharp spikes, which are in fact, which contain spectrally many high order harmonics. And if we put some metal filter on the path of this reflected light, we can filter out the fundamental, infrared fundamental, and get an attosecond pulse train if our driving laser pulse has a few cycles under the envelope, 70 cycles under the envelope. If we drive the process with a single cycle pulse, we will get an isolated attosecond pulse. So this spectrum here, this is what was obtained in my lab. This is what we now are having in my lab in Princeton. And I can tell you just a little bit about our experiment. So in fact, you can see the experiment behind me. It's not a background, it's a real lab, so I can touch it. So the experiment is really in this chamber. And here you see an active spectrometer to detect the harmonics from plasma mirrors. This is the photo of what you see behind me. So, and basically the most important thing, we have a terawatt laser, ultra fast, 25 femtosecond, pulse duration from Amplitude Technologies, titanium sapphire, and we send it, we clean the contrast with a non-relativistic plasma mirror, and then we send the pulse to the relativistic plasma mirror. In fact, we even have two of them, but now I will speak about one. So we send the pulse to the relativistic plasma mirror, relativistic because we focus so tightly that we get relativistic intensities in the focus. And then we detect and analyze reflected light from this plasma mirror here. So we have a bunch of diagnostics. We can put a scattering screen on the way of the reflected light. So the reflected light goes here. You see this is the red one shows reflected fundamental, and the blue shows a much more narrow, less divergent XUV beam. So the reflectivity of the plasma mirror is really high. It can be up to 80% reflectivity. So we put a scattering screen in the beam path, and then looking with different cameras at the scattering screen, we can, and different cameras have different filters for different wavelengths. We can analyze the reflected fundamental beam, reflected second harmonic, reflected third harmonic, and the 3/2 harmonic emission. This is something special in plasma. But fortunately, we don't really have it now, so which is a signature of that our contrast is good enough, rather good. So we also can move this screen out of the beam, and then in this case, the beam goes into the XUV spectrometer, and then this is where we can detect our high harmonics. So this is the CCD image in the spectrometer, and you can clearly see several harmonics on this. And again, this is a line out of the CCD image, raw CCD image. Important here is that here you see the so-called plasma frequency cutoff, the frequency corresponding to the plasma frequency of corresponding to the solid density of our material. important thing here is that we do get harmonics well above the plasma frequency cutoff, which proves that we really have them, the so-called relativistic regime, not other mechanisms of harmonic generation, which can also happen at solid surfaces or at plasma surfaces. So I'd like to talk a bit about the physical mechanism of relativistic harmonics. So in fact, the mechanism behind this process is coherent synchrotron emission from these relativistic electron bunches formed in plasma. So the electron dynamics in this microscopic plasma, it momentarily forms a compact synchrotron. This is a subcycle process. So if you have driving laser pulse, if your driving laser pulse consists of several cycles, so this process may repeat each cycle, but each cycle a new bunch of electrons will be formed and accelerated. If you have a single cycle laser pulse in simulations, you can easily have it, but hopefully in experiment and some boards too, then you really have this process happening only once per cycle. So what you can see here, this is a trajectory of electron near the plasma surface. So here, this is the plasma area, this is the vacuum part, and this is the laser coming incident on the plasma. So what you see that this is electric field near the plasma surface. Electric field seen by electrons near the surface. So what you see is that initially the electric field is not high enough to push the electrons, but then at some point here, which corresponds to this point, electric field becomes large enough so that electrons get pushed inside the plasma into the ionic potential, and they get pushed, and at some point the electric field goes to zero. Laser electric field. So in this case, electrons are pulled back by ions. They cross the equilibrium point. They go out of the plasma. And at this point here, they exhibit this synchrotron-like trajectory in the sense that their acceleration is purely orthogonal to their velocity. So their velocity is in this direction, and their acceleration is in this direction. And here is the time of emission of an intense attosecond pulse, or we can say intense XUV and X-ray supercontinuum, which can be described by the simple law of synchrotron radiation. So the laws of synchrotron emission immediately give us the cutoff frequency, the highest frequency of emission we can get through this process. And this frequency, what is important, is proportional to the relativistic Lorentz factor of these electrons, proportional to the Lorentz factor cubed, gamma cubed, to a cube of the Lorentz factor. This is a very favorable scaling, so to speak. So this frequency can be really, really high. So the question is, are we really going to achieve this frequency in experiment, or maybe even in simulations? Do we really see this cutoff frequency in the simulations? So what I would also like to emphasize, previous work has reported this mechanism, coherent synchrotron emission, but only for a limited set of conditions, like ultrasonic foils, reflection from ultrasonic foils, or transmission through ultrasonic foils, or highly oblique depolarized incidents. And but we found that in fact this mechanism is valid under a really broad range of conditions. So we really can say this is a general mechanism for relativistic harmonic generation. So here you see, for example, these are particle and cell simulations of laser plasma interaction. So you see trajectories for the interaction of laser with an ultrasonic foil in 1D simulation and 2D simulation. We also have 3D simulation. They all show similar results, not exactly the same, but similar. This is the similar trajectory for the very sick target, semi-infinite plasma with a steep surface and oblique incidence of the laser. And this is the similar trajectory for the density gradient in front of plasma. So these trajectories appear under a broad range of conditions. So the most interesting question is, what are the theoretical efficiency limits for this process? Should we really invest our efforts in experiments? Before doing that, we really need to know what is the fundamental efficiency limit. So it's, I'd like just to briefly note that the frequency conversion efficiency, as well as electron dynamics or attosecond pulse intensity or attosecond pulse isolation also, they are functions of many parameters. A naught is a dimensionless laser amplitude, N is a plasma density, plasma thickness, angle of incidence, gradient, if there is a gradient in front of the plasma, gradient scale length, frequency of the laser, pulse duration, and Fourier envelope phase. So the dynamics of electron bunches and their emission, they are governed by the balance between the laser driving force, which is given by the laser amplitude A naught, and the plasma restoring force, which is given by the plasma density M. So these two parameters are especially important for us. And what is also very important is that, in fact, the trajectories of plasma electrons and the emission efficiency, they actually depend on the ratio of A naught over M. This is because the balance is important for efficient interaction, the balance between the laser and the plasma force. So they don't not only depend on A naught and M separately, they depend on the ratio of A naught over M. So if we look at various spectra of emission obtained in simulations, we can see the following features. We can see that the power law fit, so these are the spectra for different laser amplitude, A naught from 1 to 1000, and A naught of 1 corresponds to relativistic intensity 10 to 18 watts per centimeter. And different colors show different conditions, spectra obtained with different A naught numbers. So these are the lowest A naught, and the red one is the highest A naught. We see that the power law fit, so this is a log-log plot. This is spectral intensity, and the x-axis is a frequency. And this is a log-log plot, so a power law would look like a line on the log-log plot. So we see that the power law fit really well approximates the spectra under most conditions. We see that for low harmonics, the spectral intensity approaches a constant value for fixed A naught over M. So the low harmonics, they all go with the spectral power law, which is different for each A naught over M ratio. So, but higher harmonics, they continue to increase with increasing A naught. So as A naught increases from blue to red, the spectra follow the power law over larger frequency range. And very important is that the exponent of this power law is a strong function of A naught over M ratio, even in the relativistic limit when the electrons, when the laser amplitudes are very high. So if we now look at the exponent, this power law exponent as a function of A naught over M ratio, we see that it, there is a frequently quoted value for the ultimate efficiency limit for relativistic harmonics, which is minus P equal to minus 8/3. It's shown by this line here, but we see that in reality, for many conditions and many interaction conditions, this power law exponent exceeds this frequently quoted value. And in fact, it looks like the minus p equal to minus 4/3 is a limiting efficiency, is a maximum um, in the power law scale, maximum power law scale. So this maximum is reached around A naught over N ratio of about 0.5. Different curves show different interaction conditions, basically different angle of incidence on the plasma. So, this scaling, omega to the power of minus 4/3, is a really promising one because it allows for 1 terawatt peak power to be produced for 1 kiloelectron volt photons if we use a plasma mirror driven by 20 petawatt laser. So this is a really great scaling. It's a really good news for relativistic harmonics. However, we should note that this scaling does not extend infinitely. It does not even extend to the synchrotron emission cutoff, which is given by the cubed Lorentz factor of electrons. So in fact, if we look again closely at one of the spectra from simulations, what we see, so next question would be, okay, we know the power law, it's really great, the limiting power law. So, but what is the cutoff frequency? Is it the frequency given by the gamma cube? No, it's not. So what we see in simulations is that under most conditions, the spectrum decays as a power law up to a certain frequency, a certain roll-off frequency, which is set by the width of the emitting electron range. So, and at frequencies higher than this frequency, electrons do not emit coherently anymore. And due to the interferences, the frequencies, interferences of emissions of the individual electrons in the bunch, starting from this frequency, the power law decreases and the spectrum decreases as omega to the power minus p minus 2. And this happens until cutoff frequency given by synchrotron emission laws, which has a cutoff proportional to the cubed Lorentz factor of relativistic electrons. So what it shows us that the cutoff frequency for the relativistic harmonics really depend strongly on the bunch width and actually bunch shape. But in simulations, we see that the shape of the bunch has a sharp leading edge and can be well approximated by a step function. So if we look at other spectra for higher laser amplitudes, we see again that the same behavior, that there is a spectral power law, which is given by minus 1/3 power exponent, and then starting from this frequency roll-off, which is given by the bunch width, the power law gets steeper, but it's still a power law, and then it falls off exponentially. So if we assume the electron distribution in the bunch is Gaussian, we get a much steeper spectrum. So perhaps I will conclude at this point. And so what I want to conclude with, so I'd like to show you this map of powerful coherent radiation sources. So here by different points, various sources of ultra-fast powerful radiation are shown. So for example, here are all the infrared lasers, titanium sapphire lasers, for example. This is many terawatt systems, and our Princeton system is here. And this is again a plot showing power as a function of wavelengths. So here you can see these are the free electron laser radiation sources, and these are the high order harmonic generation sources, gas harmonics and solid harmonics. So where is our minus first third scaling law for theoretical efficiency limit for relativistic harmonics here. So it's here. So if we assume that plasma mirrors are driven by a 10 petawatt laser, then the minus first third scaling will give us this. So we see it looks really nice. And if we compare with the previously quoted value 8/3, it gives us minus 4/3 gives us 4 order of magnitude larger power at around kilo electron volt photon energy range, which is really great, at least comparable to the radiation produced by the X-ray free electron lasers. So what's also important is that, so these are the spectrum efficiency of individual harmonics. If we sum up these harmonics and create an attosecond pulse, so its intensity can potentially be even higher than the driving laser field intensity. So this is pretty impressive, I think. So with this, I would like to conclude, and so I would like to acknowledge my team at Princeton, our collaborators, the particle cell simulation code development team, and thank you very much for your attention.
Thank you. Can you see me? Oh, no. Can you see me? Thank you very much for this. I cannot see me. No.
I should stop sharing.
Oh, you see me. Okay, now. Okay, cool. Thank you very much for the nice talk. We have not a lot of time for questions. I have just one question. You talk a lot about the scaling of energy. What is about the pulse duration? What can you do with this? You will have a train of attosecond pulses. So what will be the individual pulse duration when you have a setup like you presented today?
Well, it's an excellent question. The pulse duration depends on how many harmonics do you include in the pulse. You can select by different filters, but simulations say it can be transform limited. So it's really given by the width of harmonics, and harmonics are phase locked. What is an experiment is still have to be understood.
Okay, thank you. So